So now let's start and continue, or maybe continue from where we were. And in today the topics which I would like to cover, they will include this topic I had started in the last class, equivalent forces. I'd like to talk about that. Then from here, we will move on to the concept of simplest resultant. So both these things are part of chapter 3, and then we will move on to equilibrium, of a rigid body, which is chapter 4, and in this we will start with the concept of a free body diagram, and there we will talk of reactions and supports. That is the main thing which will be new. Then we will talk of equations of equilibrium, and these equations we will do in 2D as well as in 3D, and then we will talk of statically indeterminate systems, and finally we will talk of two force methods. Now here, equilibrium of a rigid body, actually when I say, will include equilibrium of connected rigid bodies also. That's what it is. Okay, so let's start without much ado about the topic where I left you last time, and that is equivalent force systems. And you must have done problems of this in your tutorial classes already. I had discussed this concept in the last class, and what we said was that if we have a body on which we have some forces which are acting, some couples which are acting, then the question we pose is, can we replace the forces and couples by a single force and a single couple? That is the basic motivation of doing this, and the reason for that is quite obvious. We have many forces which are acting on a system. Then what we want to say is, we want to look at a particular point in the system. What is the net effect of the forces and couples at this particular point? And in particular, this may be important because the point which we are talking of could be a point of support. So therefore, if the forces are acting and if the support is able to take those forces, then it's fine. Otherwise, we'll have to modify or redesign the support. So that was the motivation of these, and we'll also say sometimes it helps us in simplifying problems. Now, what we saw was that we find the equivalent force system at a given point A. So That means whenever we talk of an equivalent force system, we will also talk of where this equivalent force system is acting. Is it point A or point B or point C? And the force system, as you will see, will change or may change depending on the location of these points. So therefore, the point which we are talking of becomes important. Now, your original force system consists of what? Forces and couples. We have to find the equivalent of these, let us say, at a point A. So let me mark this point here. This A could be anywhere. It could be on the body, it could be even away from the body. If it is away from the body, we use the concept of what is called massless extension of the body. There is no mass, but we extend it and assume that other point also to be a part of the body. That is mainly done in dynamics. In statics, we don't do that, but that is done. So now we have the system, and what we saw in the last class was that if we have to shift the forces to point A, then each force is shifted by two components. One is the force. The force gets shifted as it is, and we also add a couple, which is the moment due to the force about point A. So this is how we shift forces. Okay, so let me just write this down in brief. So each force, when transferred oblique shifted to A, results in two components. Let me say Fi. First component is a force which is equal to Fi, and the second component is a moment which is equal to Ai cross F, where Ai is the vector from A to the point I where the force I is at. Is that clear? So we will shift all the forces like this. So therefore the total, so the net effect is equal to sigma I is equal to 1 to n Fi. This is 1 and so net F, we have moment which is equal to sigma I is equal to 1 to n So this will be the effect of all the forces at point A. Then we have the couples. What do we do about the couples? Couples directly get shifted to the point A without any change. We have already seen why does this happen, because the couple is formed by two opposing forces, and when you take the moment of a couple, it is the same about any point in space. So if I take a moment of a force F1 and a moment of a force F minus F1 acting at some distance about point A, it will be the same about point B, it will be the same about point C, so therefore it will be the same couple. So therefore this is the net effect of F, and the net effect of couple, net effect of couple is that the couple Cj is shifted to point A as it is. That is why couple is also referred to as a event. So this is how we will shift. Is this clear? Does everybody follow this? Now, the problems which it comes when if it's a problem in an exam or in a course or in a homework, it may be just, see what you do is, look at a single force at a point. You shift that, you write the vector value. And in this course, I think the best would be, so far, I know you have been used to looking at things in a physical way. And you try to calculate moments by looking at the perpendicular distance to the line of action of the force. But your intuition, I'm not saying you should throw that away. It should stay. But this works well for planar problems. For 3D problems, you will find that the position vectors will have all the three components. And if you try to directly find the moment without using the vector notation, you will end up missing out one or two components, or you may not be able to calculate the distance properly. So the best thing in three-dimensional problems is you calculate the position vector of each of these points, and you write the force as a vector. And wherever you have to find the moment, you just take Ri cross Fi. So you just individually, mathematically take the cross product and find the moment. And then you will get it in vectors. You do it for all the forces, add up all the I, J, K components, that will give you the final answer. And in equivalent problems, equivalent forces, you will always find that the solution or the problems which are there, you will have two components in the answer, a force and a moment. Is that fine? So now this is how we have done. So now using this method, I can find the equivalent of this force system at point A, I can find it at point B, I can find it at point C, anything I can find. There's one more thing I told you in the last class. If you have found the equivalent at A and you have to find the equivalent at B, what do? You don't start calculating about B all over again. What you do is, you take the equivalent at A, whatever you have got, and you shift that to B. Because now at A, you will have just a single force and a single couple. The couple will shift as it is. The force will have two components. One component is the equivalent force, which will be the same force at B. And to the couple, you have to add BA cross the resultant angle. So that part will be added to the couple when you shift it to point B. So you need not do these calculations all over again. Okay? So that is about the equivalent force systems. Now, the next thing which we want to find out is, so therefore totally when we say, so equivalent, I'll just sort of formally finish what I had started. Equivalent of force system has two parts. Part A, F is equal to, it's at the same, I'm sort of repeating this again and again, but in this part I have not written the total thing. The net part, which I can say as a CR or a total couple you can call, or the resultant moment, this will be equal to sigma AI plus Fi plus so you add both the moments. I have written these separately, I have combined this here. Now from this, next comes the concept of what we call is the simplest result. What we have said is, what we have shown so far, that we can shift things to a point and we will have a single force and a single couple. Now, next we try to ask a question. Is there a particular point on the body where the equivalent will be only a force or only a couple and not two things? Is this always possible or is it not possible? And if it is possible, then how do we locate that particular point where the equivalent is just a single force? If the equivalent has to be a single force, what will that force be? If there are 10 forces acting on a body, you try to find the equivalent at a point A. In general, you will get these two. Of course, the couple will not be there. Okay. Now, what I want to say is there a point B on the body where the equivalent is only F. Clearly the equivalent has to be sum of all the forces, because we cannot get away with the forces. All the forces which are there, they have to act. That means we are trying to find a particular point B on the body where CR is equal to 0. If we can find this, then we will say this is the simplest resultant. But then mathematically, if you look at it, by making it simplest, we have not really mathematically reduced our problem. Why? Because the simplest resultant, with that, you have to say which point it is. When we do it like this, it could be any point. But when we talk of a simplest resultant, then the freedom to choose the point goes away. It has to be a particular point or a particular line. Is that clear? Okay. So now let's try to see how do we find the simplest resultant of these systems. So now what we do is, when we try to find, so we work out what is called now for a general system, I have introduced a new term which I will explain. Probably you know of this word in a different sense. From a plumbing terminology, we know what is a wrench. Now, what we want to find is, what is, for a general system, the simplest resultant is a wrench. What do we mean by a wrench? Wrench is a system where there is a force and couple such that both have the same direction. So what's the meaning of this? That suppose if in a system, or there is a system where a force is acting, and at the same time on the system I have a couple which is acting. Now this I have shown as a curved arrow. So when I curve my fingers of the right hand along with the arrow, I get the direction. Now in this case, the direction turns out to be opposite of F, but it is still parallel to F. So a wrench is a system where force and a couple act, but both of them act in the same direction. That means there is no component of the couple which is in the plane perpendicular to it. So here it will be here. No component of couple in plane perpendicular to F. Where do we physically encounter such a situation? Drilling machine, right? When we have a drilling machine, in a drilling machine, when you drill a hole, where do you apply the force? In the vertical direction. Suppose if it's you're drilling horizontally, and the drilling machine, the couple which is acting, it is also such that its direction is in the vertical direction. Another simple example, screwdriver. When you are plugging a screw in the wall, then the direction of the force and the direction of the couple is both the same. Is that clear? So this is what we call as a wrench. And what we can show is, and what I will show, that equivalents of a force system, a general force system, we can reduce it to a wrench. Okay? And this is sort of very straightforward to show. But before that, this is for a simplest system. Let's see There are two special cases. First, let's talk of what is called coplanar force system. Here what happens is, forces act in the same plane. Somewhere, okay. This is the page entry came before, so anyway, I'll correct that. Put up the lecture. In a coplanar force system, forces act in the same plane. That means we have a plane. Let us say, let's call this plane as the XY plane. So we have I have forces F1, F2, F3. They could have any orientation, but they are all along X, Y plane. And if there are any couples, then the couples if there are any couples, they are along the Z direction. That means why do we call this as a coplanar force system? Because these couples, if you realize, if a couple has to be in the Z direction, then the forces which are causing the couple, they have to be in the XY plane. So that is why we call it as a coplanar force system. Now here what happens is, if you look at this, the equivalent of the force system at A is Fr is equal to sigma Fi, and a Cr is equal to sigma Ai cross Fi plus sigma Cg. So now, when you look at the forces, what will be the components of the resultant force? It will be along I and J. Because all the forces are along I and J, so when you add them up, you will get only I and J, no K will come. Similarly, when you look at the couple resultant, AI is in the XY plane. So that means its component will be I and J. The force is also in the XY plane, so its component will be I and J. So when you take a cross product of these two, what will you get? Only K. I cross I will give you 0, I cross J will give you K, J cross I will give you minus K, J cross J will give you 0. So this will be in the K direction, and that is why we have insisted that all the couples which are acting also have to be along K. So these will be along the K direction. Now this is the resultant at point A. Now if I'm able to now get the correct place. It's still insisting to this back here. Okay. So new page is refusing to come at the place where I want it to come. Okay, so let me continue. So if I have it like this, so this is the resultant force and the resultant couple. Then CR is not equal to 0, what we can do is we can shift the system to a point B such that AB cross FR is equal to minus of CR. At point A, the resultant was CR. Now what I do is, I find the equivalent at a new point B, such that at the new point B, AB cross FR is equal to minus CR. It will be BA, sorry, that's right. So, thank you. You know, I made this, I deliberately wrote it wrong because I wanted to see if somebody was awake in the class or not. So that is how we come out with solutions. So this is, so BA cross FR is equal to minus of CR. Okay. So that means now when you shift this to a point B, at point B, what will be the net couple? It will be CR minus CR, which will be 0. So that means at the point B, the resultant will be just a simple single force. So that is how we shift this to the point B. Now, from here you will notice that suppose if there was a couple component which was in the xy plane, that would not have got cancelled. Only that is why we insist on a parallel system of forces. Okay. So this is what we have. Now here, so if there could be a second case in this case where if FR is equal to 0, then in that case the resultant is just a couple CR, and then this is the simplest resultant. About any point it doesn't matter. If this force system eventually is only couples, then the couple will be the same about all the points. You just have to add the couples, and that itself is the simplest resultant. Or we could have a special case which we call as a null system, or we could have a case where both FR and CR at point A are 0. That means the whole system is in equilibrium, as we will show it. There will be no forces, some is 0. This is what is the null system. Let us have an example here. I think we have been doing too much theory. Let's take a simple example. Let us say we have a force F1 is equal to 6i plus 3j, and it acts at 8, 2 meters. We have a force F2 is equal to 10j newtons, which acts at 5, 3 meters, and we have a couple C1 is equal to minus 30k newton. So these are the different forces, and we have to find the simplest resultant. So these forces are given to us, these are acting on the system. Find this second part. Even if it is not given, should be implied. Because once I am using the word simplest, then the line of action or where it is acting Has to be specified, otherwise your answer is not complete. Because it's the first time we are solving this problem, that's why I explicitly write indicated slide function. Or the second type of problem could be find the equivalent force system at point 1, 2. That would be another problem, a different type. But here when we ask for the simplest resultant, so here to find the simplest resultant, first thing is let us try to find out what is in simplest resultant. We first try to work out what is Fr. So Fr will be equal to F1 plus F2. That means it will be equal to 6i plus 13j newtons. Okay. Now, because we know this is a system of parallel forces, that means we should be able to find a point where this force system is acting such that there is no couple there. How do we find that? And for that, what we do is, let's try to draw a simple figure, which you need not do, but if this is our xy plane, we have this is Fr, 6i plus 13j. It is a vector with both I and j components positive. Now, what we say is, let us, if, now this, because this is a force with a directed line, it is going to act along its line, and if I extend its line of action, now since the final answer is only Fr, its line of action is fixed. It is along the line acting along Fr. So now what I can find is, either I can find the x-intercept or I can find the y-intercept, and that will give me the answer. Because the line has to be the same. So therefore what I can say is, to work this out, I could say let Fr act at x bar comma 0. Okay. So now what I will have is, so the moment due to Fr will be equal to x bar I plus 0j plus Fr. Okay, I know Fr, I don't know x bar. What must this moment be equal to? This moment must be equal to the moment of the original system about the origin. So this must be equal to, so this moment, let's say this is m1, m1 must be equal to, f1 is 8, 2, so the moment due to is equal to 8i plus 2j cross 6i plus 3j plus 5i plus 3j cross 10j minus 30. So this must be equal to m1. Is that clear? That I have taken the moments due to individual forces. This is the moment due to f1. This is the moment due to f2. This is the couple. Sum of all this must be equal to whatever is m1. And in this, you will find I have only one unknown, which is x bar. Fr is already known to me, so therefore I will be able to find x bar. See now, you may ask the question, why did I choose x bar? I could have chosen any arbitrary point xy along the line of action. I could have done that. I could have chosen y bar also. Then what would have happened? I would have got 0I plus y bar j cross with fr is equal to this. If I would have done that, I would have got this thing at this point. I would have got the value of y bar. And you realize x bar and y bar are not independent. Why? Because x bar and y bar have to make an angle which is the same as the original force. So that is why either you find x bar or you find y bar. Or maybe you can find any arbitrary point xy along this line of action. But then that point you know has to be related to f. It has to be. So therefore we normally choose either x bar or y bar and find this. Okay? So this is how we find the force system for coplanar forces. Okay? So now the next thing which I will do, then we have a second case. Which is that of parallel force system. In this case, what we have are and n parallel forces Fi I goes from 1 to n, and what we say Fi is equal to f sub I a. That means all the forces are parallel to each other. Okay. An example of this is the weight acting on the body. Weight acts at all points, but so that's a system of parallel forces. All the forces are one. So we choose the z-axis as the axis where the forces are. Now, in this case, if the couples are there, actually the couple part is just to make it more general. Generally, then the system could have m couples whose plane is parallel to. Normally, you will not encounter these couples. So here we have couples C1, C2 up to Cm, which have only I and j components. The couples have only this. So now here when we work out the resultant is Fr is equal to sum of all the forces. So in fact here you can also add the forces in a scalar algebraic way, and then because all the forces have the same component k, so therefore I can put a bracket here, k can be even outside, it doesn't matter. Okay, and in this case the couple resultant which will come out, let us say we do it about origin, so this will be equal to summation I is equal to 1 to n xi plus yj crossed with fik plus sigma over g. So now let's try to see what are the components this couple has. Forces have k direction. What will be the direction? I cross k will give me j. J cross k will give me I. That means this will be having I and j components. and the couples also have only I and j components. So that means in this case, the couple resultant which I take about any point, that will be having only I and j components. So this couple resultant will have I and j components. So now what we do is we shift this CR or shift the force system to a new point which I call as x bar y bar, such that CR about the new point is equal to 0, and here therefore the resultant will just become equal to Fi. So once again, how will we carry out this exercise? Exactly the same as before. About the origin, we say let the equivalent simplest resultant act at a point x bar I plus y bar j. So we calculate the total moment about that, and that must be equal to the moment of the original system about the origin. Now here what will happen is you will realize there will be two unknowns x bar and y bar, not a single unknown x bar, because this is now a point in the plane where effectively the force is acting. So equivalent force, when you calculate the components, here you will have to calculate, what you will get will be both x bar and y bar. And it is feasible from the equations, because when you write this vector equation, it will have two scalar components, an I component and a j component, and there will be two unknowns x bar and y bar. Okay? So you will be able to find the unknowns here. Now in a general system, so these were the two special cases. In a general system, we have FR and CR, and we do not put no restriction. Now what we can do is, the CR which comes, we can divide it into two parts, a CR parallel and a CR perpendicular, where CR parallel is parallel to the resultant force, and CR perpendicular, obviously as the definition says, this is perpendicular to the resultant force. So this is a general system. You calculate the resultant at any arbitrary point, you will get FR and CR. And what we do is, so that means what we are doing, whatever is this couple, we divide this into two components, a component parallel to the force and a component perpendicular to the force. Now, this is about a point A. If I start to shift around the point B, I can find a new point B where I can cancel out CR perpendicular. Because when I take AB cross FR, I can only play around with the perpendicular component of CR. But I cannot do anything about the parallel component of CR. So that means, at best, what I can do is, I can shift my system to a new point where I can get rid of CR perpendicular, but I cannot get rid of CR parallel. And at that point, what will be the equivalent force system? FR and CR parallel, which is a wrench. And this is what I started off by saying when I said that the simplest equivalent of a general system will be. Now, as far as the course or the examination type of problems go, we will not ask you problems directly involving wrench. Maybe there may be one or two problems in the sheet, but at least in the examination, at least the minors and majors will not directly check you about wrench. But other things will be there, that what the equivalent force system, parallel force systems, and what is the simplest resultant, and parallel or planar force system, those you should do. So this is the this thing about. So maybe I can just complete the argument to CR parallel. That means at a point A, I have FR, I have CR parallel, and I have CR perpendicular. So this is what we can now do, is we shift the system to a point B, where so basically what it will go, okay? That we shift the whole system, given a system at A, we shift it to a point B, where VA cross FR, which is perpendicular to FR, and at point B, VA cross FR will be equal to minus CR perpendicular. So that means they will cancel out, therefore the resultant at B will be just FR and the CR parallel, which is what we have called as a range. So this is the proof that for a general system we have a range. Okay. So this is for the equivalent force systems. Now next what we do is we talk of equilibrium of a body. Now, what do we mean by the term equilibrium? Resultant force and couple are zero is something which will cause them. But what is the physical meaning when we say a body is in equilibrium? It is in a state of rest. I'll talk of uniform motion also. So, by equilibrium of a body, now see all these, when we talk of equilibrium, that means we are talking of a body which could be moving. By equilibrium we mean a body which is at rest. Now, as somebody said, that means all parts of the body, when we look at it, they are not moving. Now this is with respect to the frame of reference in which the body is being observed. Okay. So, look, when we talk of equilibrium, we will talk of equilibrium with respect to what we call as an inertial frame of reference. What do we mean by an inertial frame? Does a frame like this actually exist or not? We probably don't know. And inertial frame actually comes from the first reference of inertial frame comes when we talk of Newton's laws. And in Newton's laws, when we talk, what we do is we talk of forces which are acting on a body, and we talk of their relationship to the rate of change of velocity or the rate of change of momentum of the body on which forces are acting. And what we find is Newton's law means something which you cannot prove. It is a statement you see repeatedly, you observe it is correct, so that's why you say this is a law. We can't prove it. It's a postulate. It's something which we have imagined. But it's not such a bad imagination, because this is what we observe. And in Newton's law, what we find is that Newton's law are valid if the movement of the body is being measured in a frame which is at rest, which is at absolute rest. And such a frame is what we call as inertial frame. What we also find is a second frame, which is moving with a constant velocity with respect to an inertial frame, is also an inertial frame. As long as the frame is not accelerating, then the other frame is also an inertial frame. And that is why when we talk of equilibrium of a body, then we say that the body is at rest or it is moving with a constant velocity. Constant velocity means we automatically say it is moving along a straight line with constant speed. Because if the body is moving on a curved path, even with a constant speed, its acceleration is not zero. We will talk of accelerations and velocities in probably just before minor one when we talk of the kinematics of a particle. Right now, I'll just, some of kinematics you are probably exposed to, some may not be exposed to, but we'll just stop at this. So therefore, when we talk of a body, so that means when we talk of equilibrium, we'll talk of equilibrium with respect to an inertial frame of reference. An inertial frame, if a frame, inertial frame is supposed to be a frame which is absolutely fixed. Now, you may say, we take surface of the earth as an inertial frame. For most practical purposes, it works correct. But if the rotation of the earth cannot be neglected, because we know actually earth is rotating, so a point on the surface of the earth cannot be an inertial frame. But we take it as an inertial frame because the errors which we make by neglecting that are minimal, and we can let go with those errors, we can live with those errors. If there are applications where those things, the rotation of the earth becomes important, then we will fix our frame to the center of the earth, which is not rotating, and we call that as an inertial frame. But actually, center of the earth is also rotating. Then you say you fix it to the center of the sun. That would be an inertial frame, but then sun may also be rotating. So therefore, whether a frame is inertial or not depends. Maybe there is no inertial frame which exists. But if a frame, we call it as inertial, then for our purposes, the movement of that frame or the acceleration of the frame has been written. And see, this is something which you have to keep on doing in engineering. You will never find ideal situation. The equations which we write will always be for some ideal situation. But actually, somewhere they may be violated. And therefore, see, for example, even classical mechanics at one time one thought was fine till we entered the relativistic domain. Then we realized that even mass is not constant, which we assumed here. So these sort of things could be there. Now, so therefore, what we have is, and this I will state here without proving right now because we are not doing dynamics, and that a body is in equilibrium if all parts of the body are in equilibrium, and the equations, this is what some of you answered, governing equilibrium of a body are, the equations which govern would be A, sum of forces is equal to 0, and B, sum of moments the governing equations of equilibrium become, for a rigid body, sum of forces is equal to 0 and sum of moments about a point O is equal to 0, where we qualify that point O is any fixed point. The point should not move, and this point could be a point on the body, it could be a point fixed in space, it could be any point. And these equations will give you the equations of equilibrium. Okay. Now, if you look at this in two-dimensional context, the first equation will give you two scalar equations. In three-dimensional, you will get three scalar equations because you will have a component in x, component in y, component in z. Similarly, when I look at the moment equation, if I have a two-dimensional system, I will get only one equation. It will be, if the forces are along x, y, the moment equation will give me only a k component. Whereas, if it's a three-dimensional system, then this will give me three equations. Basically, I will have moments about O is equal to 0, and I can look at them as, in the last class we did moment about an axis. So if I have top of O, let's take the simplest case of Cartesian axis, that means the x component, the y component, and the z component of moment about O are. So this will give you another three equations in case of a three-dimensional system. So total number of equations which we will get, if it's a two-dimensional system, will be 3, and three-dimensional system will give us 6. So let's write this down. In a 2D case, this will imply sigma fx is equal to 0, sigma fy is equal to 0, and k component. So in this case, we will get 3 in a 3D case, I will get a total of 6 scalar equations. Now, let us look at an exercise of what we call drawing a free body diagram. When we, to solve any problem which involves forces and moments, what we have to, the first step in solution, the first and the most basic step in solving any mechanics problem involving forces and moments is drawing the And actually, if you look at our engineering approach, the engineering approach which we use is something very similar to drawing the free body diagram. Because what is the first step which you do in drawing the free body diagram? You have a body which may be connected to the environment or to some external things. What you do is you isolate the body. That's the first step. And this is what we do in any engineering system. I want to design the car. I will isolate the car. I will just look at the car, forget everything else first. So the first step in drawing the free body diagram is that we isolate the body. And from surroundings. So we have body, which was, so for example, let's say, I'll just show it. Suppose there is a bar which is pinned to the wall, on which its weight is acting a force F. If I have to draw the free body diagram of the bar, what I will do is I will isolate the bar from the surroundings. That's the first step. Draw the bar alone. Whatever is happening internal to the bar, I don't care. That is not a part of free body diagram of the bar. So if there is something internal, two forces are acting, we don't care. Next, what we do is we make a physical inspection all around the bar. And whatever external forces are acting directly, first we will show them. So that means I isolate this. I show the force F1. I show the weight W. Next, when I come to this corner, I see I have isolated a pin. So now what I have to do is, at this point, I have to show the effect of the support. I have to show whatever forces or moments are being caused by this pin because I have removed the pin. So its effect has to come. And this is something which is very important, that this is what the surroundings are doing to the system. They have to be properly monitored. Somewhere in our engineering, what we have missed out is what the system does to the surrounding. We don't care about that. We only care about our system. For example, I want to design a car. I will just see how fast the car goes. I will not care what it is doing to the environment, which should also be a part, and I think that is where we have gone wrong. Because theoretically, when we have studied our engineering, we only talk of the system. We focus too much on the system. We do not model the effect it is doing to the environment in a proper way. We only model how the environment is affecting the system, and we try to minimize the bad effects of that. What the system is doing to the environment, those effects should also be minimized, and I think that is what we would call as holistic engineering rather than just a systems. But anyway, that is a more of a philosophical discussion. Let's leave it for later. Now, I have a pin like this. What sort of effect will come in terms of force and moment at this point? And for this, the best way to see this is, physically, you try to move the body in two type of ways. You try to move it linearly across, if it's a planar problem, along x and y, if it's a 3D problem, along x, y and z. So now, if you try to move this bar along the x direction, so let me write this down, I don't think you'll find this in books. To model effect of support, we move the body a B rotational. And what do I mean? So at this point now, let's talk of a 2D system. If I try to move the bar along the x direction, will the pin stop it or not? It will. If I try to move it along the y direction, will it stop it or not? It will. The pin will not let the bar move up and down. So if there is a linear restriction along a particular direction, a force will come because of the support. Okay, so that means at this point I will get an unknown or a support or a reaction along the x direction and a reaction along the y direction. Is that clear? Because if I try to pull or push, if I try to pull it along x direction, the pin will stop it. If I try to move it along the vertical direction, the pin will stop it. That means wherever, if there is a restriction of linear movement, then there is a force in that direction by the support. Okay? So that means in this case when I draw this, let's draw the free body diagram again, and I will focus now only on this point. I will have a reaction in x direction and a reaction in the y direction. Okay? Now this is a planar problem. If I try to rotate the bar about the z axis, will the pin stop the rotation or will it not stop the rotation? Assuming it is a frictionless pin, then the pin will allow the rotation. Is it or no? Is this point clear? We try to rotate about the pin at that point where the support is. I try to rotate the body about z axis. Will it stop or not? It will not stop, assuming that there is no internal friction in the pin. So that means there will be no moment which will come in here because of the pin. Because it can rotate about the z axis. If it cannot rotate, then a moment will come. But because this pin is not allowing any rotation about it allows a free rotation about z axis, there will be no moment. Is that clear? So that means the unknown supports when I draw the free body diagram, because of the pin, I will get only Rx and R. Now let us look at the same pin. But now let us say we have Fz, this is the x direction, this is y, this is z, so we have Fy here, we have an Fz here, and I have something like this. So now I have the same pin, but I have a three-dimensional forces which are acting. It's not a planar system anymore, no longer xy, I also have a force in the z direction. So now this becomes a three-dimensional system. Now when I look at the pin, what does the pin do? Does it stop the x movement of this? If I linearly try to move, will it stop? Yes. What about the y direction? Does the pin? What about the z direction? It will also stop. That means what type of a force will come in the free body diagram here? Rxi plus Ryj plus Rzk. So when I draw the free body diagram of the pin here, for this three-dimensional case, I will get here Rx, Ry, Rz. Now unknown forces I can show with any orientation, plus or minus. These are unknown. When I finally solve the problem, is the attendance sheet moving around? Where is the attendance sheet? Well, फटाफट चलाओ class. This whole, why does it stop midway? Okay. Now let us try to see. With the same pin, if I try to rotate the system about the z-axis at the pin, will it allow a rotation or no? About the z-axis, will a rotation be allowed? The bar can rotate. Now what about if I try to rotate this bar about the x-axis, will the pin allow a rotation? It will not. If I try to rotate it about y, it will not allow. So now that means what else should also come in the unknowns here? I should also put an mx and an y. Because the bar, because of the pin joint, for a three-dimensional case, the moments could be along x, y, and z, all the three directions. The pin allows only a free rotation about z. It does not allow a free rotation about y, or it does not allow a free rotation about x. So therefore, when I draw the free body diagram of the pin, I will, at this point, I will have rxi plus ryj plus rzk, and then I have mxi plus my. These will be the unknowns that will come at the support. Okay? Now, let's look at some of the, this is where I think, now, we look at some planar systems, different type of supports. We have support with a pin, but in this case what you find is the pin is not connected to the ground. It is kept on rollers. Okay? And different versions of these, we have 2 or 3 different versions. The second version is a link which is kept on a single roller. So that means roller means there is no friction, it can move easily along the x-axis. In this case, again there is an arc of a curve without friction, so we call it as a rocker or a frictionless surface. Now when I draw the free body diagram of the inclined bar in each of these cases, if we tend to push the bar along the x-axis, it will move. It will eventually it will not move because it is statics. But if somebody tries to move it, there is no resistance to the movement. Because there is no resistance, there will be no x component of force which will come from the support. So therefore, in all these cases, the force will be, the unknown reaction will be just a vertical force. Similarly, if you have a short link, and this I will come to when we talk of 2 force members also, or if we have a cable, then the force only will be provided along the direction of the link or along the direction of the cable. So therefore, we will only have, when I draw the free body diagram of this bar, and if it is connected with a cable, I will just show a single force in the direction of the cable. So here only one unknown will come at this point. To try to rotate it about this, it will get rotated, no moments will come. Then we have the case of a collar on a frictionless rod. So we have this rod, we have the link connected, and the link is connected, is sitting on the rod, connected through a collar which is frictionless. Or we have a pin which can move in a frictionless slot. In this case, when I draw the free body diagram of this link, if there is a movement along this direction, there is no resistance to this because of the pin. That means the only force which is coming will be a force in the perpendicular direction. There will be no force along the direction where it can move freely. So therefore, when we draw the free body diagram, we will only show a single force in that direction. Now, this is the case we have already seen. A frictionless pin or a hinge joint, or if we have a rough surface. Then what we have is, as I told you, there will be Rx or Ry. Another way of writing this is, you show that there is a single force at an unknown angle alpha. So that's the same as putting Rx and Ry as I had put in my slide. Okay? Now there is one last case which we have in these planar systems, and this is what we call as a fixed support. Think of a nail which has been hammered inside the wall, or some beam which has gone inside the wall. In fact, some of these we call as if the beam is hanging with one end free, we call it as a cantilever. So this is fixed inside the wall. So in this case, if we are talking of a planar system, obviously this will not allow any linear movement because of the support. But also, if I try to rotate this bar about the z-axis, the fixed support will not allow a free rotation. Compare this with a pin. If this was a pin, it could have rotated freely about the z-axis. But with a fixed support, it cannot rotate freely. So therefore, what we will have is, in addition to the force, I will also have a couple which will come in as an unknown reaction. So here we will get a reaction will be a force and a couple. Okay. Now, when we look at three-dimensional equivalents, there's only one more thing which comes. So we have seen these 2D cases. In case of three-dimensional this thing, we have something which is called a ball and socket joint. What do we have here? In a ball and socket joint, now obviously this ball and socket joint is important from a biological perspective also. Our shoulder, this joint here, the shoulder connected to the body, this is a ball and socket joint. Here what happens is, in a joint like this, what we have is there is what we call as a socket, and in which a spherical type of plane sits. For want of space, I have not made it vertical, I have just turned it around, but it could go up also. So this is a ball which sits in this. Now here what happens is, such a joint will hold the body fixed to this space, but it allows a full rotational freedom. This body can rotate about x-axis, y-axis as well as z-axis. But because it is fixed with the joint, it cannot linearly move along x, y and z. So when I draw the free body diagram here, what will I get at this point? I will get Rxi plus Ryj plus Rz. So in this case, rotational movement allowed, and what we have is for the reaction at the joint is equal to Rxi plus Ryj. Okay. Now there's just one more thing, I'll stop after that. If you have a class, so after एक 10 मिनट के क्लास के कहाँ पे गया extra Bharti. Okay, I'll stop. The only thing is that in the tutorial this week, you will be doing problems where you will draw the free body diagram, and after that you have to apply equations of Euclidean. That means sigma f is equal to 0, sigma f is 0.